So this is a review. What happens first? Good. The neutron strikes the uranium. Now, I'm going to tell you right now, because you don't have to know every single detail. Like yesterday we talked about the mining and the ore and the forms of uranium. You have to know uranium-235, okay? Eventually, I know it's going to lead to knowing plutonium and knowing isotopes of uranium because I feel like that's coming. But right now, you just have to know uranium-235, okay? So even though chemically it's not going to make perfect sense, just go with it, okay? So we've got the uranium-235 got hit by a neutron. What happens next? It splits into daughters, and then it releases massive amounts of heat energy, and 2 to 3 neutrons are produced, okay? So then what happens? We split already. So the neutrons were formed, they hit the daughters. And then what happens? It repeats. So we're going to have more what? More daughters, more neutrons, and more heat, and uncontrollable chain reaction. You want to add that. The idea behind fission gets applied into a nuclear power plant. And this is what a nuclear power plant function looks like. It looks similar to what? Coal. The biggest difference is going to be right here, okay? And I'm going to explain the differences first, and then we'll go back in and explain the whole process. So the biggest difference is the fact that there has to be a containment structure. I'm going to just tell you this. In Chernobyl, which somebody mentioned yesterday, there was no containment structure, okay? So what do you think this containment structure is made up of, and what's its purpose? To contain radioactivity. And if you're going to be a structure that's going to be exposed to massive amounts of radiation, what do you think your material is going to be? A lot of concrete and better than metal. Or the highest form of steel. Good. So we got steel and concrete. And they have said that the size of the walls of a containment shell could be as thick as this room. That's how much steel and concrete it takes to build this shell. Without this shell, the heat can get easily released or seep out of the power plant and affect every employee in it as well, okay? So this is an important thing because it houses what we call the reactor core. This is the reactor core or reactor vessel. It's another name. What's in there is called fuel rods. What do you think is going to be inside a fuel rod? Uranium. And they're going to produce what? Heat, but they're going to undergo fission, right? So they undergo fission, not really produce fission. Let's change that. Or they have uranium undergo fission, okay? Then what do you think the control rods do? They capture the neutrons to control the excessive amount of heat that's being produced during fission. Both of these things are inside the containment structure, okay? But in the reactor core or reactor vessel, I'm going to bold print this word, are fuel rods, so if you want to number them, and control rods. So if you have a question, what's found inside the reactor core or reactor vessel, the answer is? Good. And then in the containment shell, you also have a coolant. It travels through the reactor core. It's not really in the reactor core. You see it here. This is the reactor core or reactor vessel. But it travels through there or it's part of. What do you think it's going to do? And what is it? What do we see in there? Water. And a lot of other liquids that they mention, you don't have to know, are added to do what? Yes, to cool. Remember what happened? I'm going to pause. See that? So that is an actual nuclear power plant. And you could see the fluid in there, right? Those are your fuel rods right here. And those are your control rods. And fission is happening every time you see that flashing. So how does this happen? Is uranium is placed in what? So this is a more in-depth to the last slide we just had. In the fuel rods, which are located in what? The reactor core, which is inside the containment shell, okay? And the uranium is placed in fuel rods to undergo fission, but what type of energy is uranium? Nuclear, good. Don't confuse that with fossil fuels, which are what? Chemical, good. Then fission occurs, and it makes what kind of energy? Heat. So there, my energy transformations are being represented here. What happens next? Now everything is the same. Water is added to do what? Make steam, which does what? Spins a turbine, which sends what kind of energy? Mechanical. Then the turbine is attached to what? Generator, which sends electric current, which is the last form of energy. And that gets sent to your home through these transformers. Now, a condenser is another, and these actually exist in coal-powered plants. Look at the picture of the condenser. What's it doing? Good. It's recycling the water and recapturing, returning the steam back to water so that they can reuse it to cool the reactor or produce steam or whatever the water is going to be reused for. And then in addition, we have what's called cooling towers. Anybody know what the cooling towers are going to do? Look at the sentence. Blank that cannot be used for generating electricity. Heat. So once the heat can't be used anymore or there's not enough heat being produced, it's still something you want to capture because it's still energy. What are we going to use this heat for? We already talked. Remember, desalination is the answer. Good. All right. This is what a fuel pellet looks like. So again, the uranium, and remember we talked about how, somebody asked me how big is uranium, and I said like this. I was right. It literally fits in your hand like that. Now that's a pellet of uranium, which is filled with this. It's just like another, it goes through a process, and we'll talk about that Monday a little bit. But this is what the fuel rods look like, and this is what the containment shell looks like an outside view. Inside, you could see the construction and the thickness of the walls. There's pictures online. All right, so what are some advantages to nuclear energy? Again, think about why we even started with the idea of having nuclear energy. Hold on. CO2. Less CO2, really less environmental impact. I had to add this sentence, which is straight from your book. Without accidents. I love that they added that because technically, once there's an accident, the emissions, and less CO2 is just one of them. Emissions in general, less land disturbance, less effects to the environment totally in comparison to everything else, except if there's an accident. If there's an accident, the consequences are so severe, it's like, it's so bad. Yes. Is not really, high yield meaning what? Okay, good. There's a lot of supply. Good. Because yield involves a little bit more. There's a lot of uranium. As I mentioned, the way it formed millions of years ago, it left tons of it almost in all of the core, the crust of Earth. Yes. You don't have to know that. Yeah. But it has to do with the sun and radioactivity, just like all your rocks formed. And inside that rock is the decaying form of radiation of uranium, let's say, okay? But you don't have to know, like, you know how we went over how fossil fuels form? Yeah. What you have to know is that they won't reform. Whatever we have is what we have. And the chances of seeing it again, it won't happen in our lifetime. All right, what else? There's the little pellet. What about it? Look at this diagram. A lot of heat. We're not going to say efficient like we said yesterday. It's not. It is a super high heat producer, and it only takes a little bit to get a large amount of heat. But it's not efficient because of, and that's my next slide, efficient for a long time. If I taught you this class and I would have recorded my videos, nuclear was the most efficient form of energy. And then they had to start dealing with the waste. And this is why I say I'm going to introduce disadvantages today, but I'm going to talk about them a little bit more in detail. So the things we have to do to this waste starting from the waste that's produced during mining, which is called low levels. They have a medium level, which is kind of during refining, and then you have the high level waste, which is after fission. And I'm gonna go over that again on Monday, okay? But that waste is extremely radioactive, especially high levels, and it has to be dealt with, and it requires tons of energy, tons, actually like 12 to 20 years of storage using energy in order to try to reduce the amount of radiation before you can even bury it, okay? So keep that in mind. That's why it is the least efficient, because although that little pellet can produce massive amounts of heat, what you have to do after your uranium stops undergoing fission or enough fission to power a plant, this is a big problem. You also have to worry about war, even though thankfully we have not experienced anything like that, but the little pellets, once they're done undergoing fission, there's a lot of talk of reusing them because they're still powerful enough to do things. And one of them is the plutonium aspect, which again, you don't have to know, which is what they can make weapons from. So that's pretty scary. Even though there's this, and I'll talk about that too, there's this whole thing that you can't go there, but, and then nuclear accidents. Obviously something that we know exists, has happened, and is definitely a problem, because once that happens, oh, and one more thing that I didn't put here, the lifespan of the plant is definitely a disadvantage. They have a lifespan. The plant has to be redone, the reactor core has to be redone, the containment structures have to be redone, and after a while, the plant can no longer function. For safety reasons, they have to be closed down. So they have a lifeline. So if you're investing in nuclear power, you have a time on your investment. Yes?